Okay, so today I would like to tell you about some interesting relations that we have between entanglement, between geometry and thermodynamics. So these three apparently different, well, this connection is more or less clear, but the connections between these three things are all made very manifest when you consider black holes. And so we'll discuss how thinking about black holes brings some connections between these three different areas. So black holes start with the Schwarzschild solution. A black hole is a particular geometry of space-time. And just to be concrete, I'll write it. Has the usual Schwarzschild metric, which I'm sure you've seen many times. So this is describing the metric outside the black hole. Outside the horizon of the black hole, there is a horizon at r equal to rs. And this is describing the metric of the space-time outside this horizon. We'll later discuss what's inside the horizon, but for the time being, we're discussing what's outside the horizon. The horizon has an area which is given by setting r equal to rs here. And this metric looks like it has a singularity at the horizon. However, this singularity is apparent, and once you make a coordinate change, well, maybe I guess I can just continue writing it here. So in order to understand the geometry near the horizon, it's convenient to choose a coordinate. So we are going to expand around r equal to rs, and we're going to choose a coordinate rho. And here I'm going to put these factors just for convenience. And if we do this, then we find that the metric near the horizon has is completely has the following form. So it so I chose this coordinate rho so that it would be the proper distance from the horizon. So this is the metric to leading order in rho, in the coordinate rho. And what we see is that up to this factor, it looks very similar to the metric. So I'm going to just rescale the time coordinate. And so define a new tau, which is just a rescaled version of this time coordinate. And now we have this metric. And this metric is nothing else than the usual flat space metric. The usual flat space metric, where we define an analog of polar coordinates, which is rho e to the plus or minus tau. Okay. So this is just ordinary flat space, where you have the spatial coordinate and a time, now the flat space time coordinate. And then we're defining null coordinates x plus and x minus. And a line of constant rho corresponds, so this is a surface of constant rho, it corresponds to a time-like trajectory. And tau is a time coordinate along this time-like trajectory. So as we vary tau, we move along this trajectory. And this trajectory is an accelerated trajectory. Okay? And that acceleration is nothing else than the gravitational force you see when you stand at a fixed radial coordinate in the Schwarzschild geometry. You'll feel a big pull that pushes you into the black hole. And here again, you see the same as this acceleration. So the metric, the black hole metric, corresponds to rho bigger than 0. And that corresponds to this portion of the flat space region, sometimes called Rindler space. So Rindler space is nothing else than ordinary flat space, but in the analog, the Lorentzian analog of polar coordinates. Now, we see that we can go behind the horizon. There is nothing special at the horizon. Once we go to these other coordinates, the horizon is just as any other point in space. And an observer who's following a free fall trajectory would simply cross the horizon and go into this interior region. So this is only describing the geometry near the horizon. When we go further inside, we'll run into a singularity, and we'll discuss that later. But for the time being, we are going to remain outside the horizon or near the horizon. Okay. Now it's interesting. So this simple change of coordinates took many years, and since Schwarzschild first proposed the black hole solution, until it was finally understood that you could do this simple change of coordinates and nothing special happens at the horizon. Okay, so now when you consider the effects of quantum mechanics, there is an interesting phenomenon that happens, which is the fact that these observers who are following these accelerated trajectories actually see a temperature. Okay, so let me discuss this in some detail. So first, we'll discuss this phenomenon just in flat space. So we'll take flat space, and we'll describe flat space as seen by these accelerated observers. Okay? So we just discuss ordinary physics in flat space as seen by these accelerated observers. So we'll just simply consider a flat space with this metric. Okay. So that's what we want to consider, and we want to consider a quantum field on this space. Now, let me try to first understand what happens in Euclidean signature. So let's make this tau Euclidean, and then we'll make it Lorentzian again at the end. So if we made it Euclidean, we would find this metric now with this Euclidean time coordinate. Okay. And this is nothing else than, well, this looks like the ordinary polar coordinates in the plane. So we have a Euclidean plane now, and tau Euclidean is just some coordinate that goes around the origin. Okay. Now, we would have exactly the plane if we chose this tau Euclidean to be periodic. Okay. So we have the ordinary plane if tau Euclidean is equal to tau Euclidean plus 2 pi I, plus 2 pi. Okay. And vice versa, if we want that this Euclidean geometry is exactly the plane, then we need to take this tau Euclidean to have period 2 pi. Okay. Now, so we are considering the quantum fields on geometry like this, which has some coordinate which we are interpreting as Euclidean time, and this coordinate has period 2 pi. Okay. Now, when you have in Euclidean space a coordinate, a time coordinate that has period 2 pi, that has some period that is periodic, then you are having a field here at finite temperature. So if you have Euclidean time equal to Euclidean time plus beta, right, then it means you are considering a quantum field theory at temperature beta. Okay. in other words, considering the physics of the quantum fields on this geometry is equivalent to taking the Hamiltonian that describes the quantum fields on this original geometry and computing the trace of e to the minus beta h, where h is the Hamiltonian associated to translations in time, and beta is the temperature, which in this case would be 2 pi. Okay, so that's somehow a quick derivation of this effect of this of the fact that this observer would see a temperature, and there are many checks. I mean, if you don't believe this derivation, you can go through longer derivations and you find the same result. And it really means that if an observer who is in this trajectory just sticks a thermometer, he would see essentially this temperature. I say essentially because he actually would not see exactly this temperature. You would need to take into account redshift factor. Notice that the tau coordinate there, so the tau coordinate here, is not proper time, but it's some arbitrary time coordinate. And so if an observer is sitting at some particular value of rho, his proper time is given by rho times this t, and that puts an extra redshift factor, which says that the proper temperature, this is the temperature that a thermometer would measure, would be 1 over 2 pi. So that's the beta we just calculated. And then the 1 over rho, which comes from this redshift factor, the change of units. Okay. So observers who are moving. So if we compare two observers, one following this trajectory and the other one at a different value of rho, this guy here would see a higher temperature, okay, and would also feel his more accelerated. His acceleration is also bigger, so you can check that the proper acceleration of these trajectories is also proportional to 1 over rho, okay, and proportional to the temperature. Okay. So this is in units where the speed of light is 1. Now, of course, for ordinary accelerations we are subject to in everyday life are accelerations which are very, very tiny and lead to very tiny temperatures, and so this effect is difficult to measure. However, now I'd like to make a comment which is one aspect which is sometimes confusing about this effect, and it's the following. So it is the fact that in order to see this temperature, it's important that this horizon really exists as a horizon and that the space-time is smooth there, right? I mean, if for some reason you were to put a mirror here following also one of these trajectories, you could have a state for the quantum field which actually has 0 temperature. Okay. Now, in the case of the black hole, that would be like cutting off the space-time at a distance bigger than the Schwarzschild radius, and having some other metric there. Let's say it could be the metric of a planet, for example, and that planet could be at 0 temperature. And if you are standing on the surface of that planet, you feel some acceleration. But if you stick a thermometer, you could be at 0 temperature. Okay. So that seems to violate the spirit of general relativity that says that an observer, if he's accelerated, he should see. What he should see is independent of whether his acceleration is inertial or whether he's sitting at, or whether it's due to a gravitational field and so on. However, notice that this effect is somehow a non-local effect because the wavelength of radiation, you are going to emit is of order the temperature to the -1, and is also proportional to rho. So the wavelength of the thermal radiation is big and is comparable to the distance to this horizon, right? So the horizon for the accelerated observer. So if you modify the metric in this region, well, you might modify this effect. And this is what happens in the case of the planet that we said. So as an exercise, I suggest that you compute, you write the acceleration here on the surface of the Earth in meters and compare it to the radius of the Earth. Okay, you'll find that that distance, so the inverse of g minus 1 in meters, after you put the factors of speed of light, is much bigger than the radius of the Earth, and therefore, if we wanted to compare to this setup, we don't have the same as this setup, and therefore we are not forced to have acceleration. We are not forced to see the temperature. That's comment number 1. Comment number 2 is that how can it be that another confusing aspect is how can it be that the Minkowski observer sees 0 temperature and the accelerated observer sees some finite temperature? So how can this be? I mean, it seems that the two are in different physics. So for example, let's imagine a situation where the accelerated observer has a 2-level system. So he has, let's say, a particle with some 2 masses, which two states which differ slightly in energy, and this coupled to the quantum field that is defined here in this space. And the observer along this trajectory would see that we are constantly changing from the low level to the high level due to thermal effects, right? So he starts with one and then shifts to the other one, let's say, and then you have the high one and then the low one, etc. Right? Now, what is the explanation that the Minkowski observer would say to this, would give to this phenomenon, right? This is an objective fact that this energy level is changing. It could be 2 different particles of slightly different masses. Now, the Minkowski observer would say, well, this is, we are here following an accelerated trajectory, and we're having some coupling between this particle or this system and the field, the quantum field, the Minkowski space, and therefore, we expect some form of Bremsstrahlung radiation that is coming out of this, and due to this coupling, we see this Bremsstrahlung radiation. And so the Minkowski observer would explain this by saying that we are emitting Bremsstrahlung radiation. Okay. Or I guess you could say that whenever you see Bremsstrahlung radiation, it's a manifestation of, I mean, the observer who is being accelerated, the particle who's colliding in the LHC is seeing the Unruh effect. That's perhaps a stretch, but okay, so now let's go back to the black hole geometry. And so we're coming back here to this geometry, and we'll calculate the temperature for the black hole case. So we already said that the beta would be 2 pi if we use the time tau, and then if we use the time t, the beta is just rescaled from 2 pi by that factor of 2 Rs that we have dividing there. So that's the inverse temperature that that is defined with respect to the time t, which is the time coordinate far away. So that's the temperature that an observer far away would assign to the black hole. One important thing I forgot to mention is the following. So here we have a proper temperature that depends on rho, right? So it depends on on G00, on the gravitational redshift factor. Now, one thing you might be confused is that how can it be that if we have a system in thermal equilibrium, we have different temperatures at different positions, right? So here we have some metric. Well, this is the near horizon metric, and an observer sitting at different values of rho would see different temperatures. But well, that's might sound strange, but it's actually a true property of gravitating systems that are in thermal equilibrium. That if you have one such system, as a star, for example, if a star is in thermal equilibrium, then the temperature, so if the sun was in thermal equilibrium, which is not, but if it was, then the temperature at the interior would be higher than the temperature outside, okay? Because the G00 is smaller. Okay, and that we see also in the case of the horizon. So the equilibrium condition is that the temperature is related precisely by this redshift factor, so we can think of the black hole as a system in thermal equilibrium, and T is the temperature we would assign from far away. Again, the temperature seen by an observer who sits very close to the horizon at the fixed position, fixed radial position, would be higher. Very well. Now, this beta is also the wavelength, is of the order of the wavelength of the emitted radiation. So if you have a big astrophysical black hole whose threshold radius is a kilometer, this is a very tiny temperature. And so imagine you wanted to have a black hole that emits visible light. How big should this black hole be? Any guesses? 1 meter, 1 nanometer, 500 nanometers. What? Yeah, it should have the size of the order of the wavelength of light, right? So such a black hole. You can, as an exercise, check what the mass of that black hole would be, and you can think how much light is emitting and whether it would make a good flashlight. It's an amusing exercise. You could try it. Okay. Well, maybe I should tell you that if you calculate the mass, it's roughly the mass of a continent. So it's a little heavy to carry as a flashlight. But well, you can wonder how much light it will be emitting, right? So we have this black hole which has some area Rs, right? So let's suppose it emits light as a black body, right? So it's emitting light. Let's say we have this submicron size black hole which emits white light. You can estimate how much light is emitting and whether you would actually be able to see it. You won't emit very much light because it's very tiny. So a black body which is so tiny doesn't emit a lot of energy. But anyway, so those are amusing calculations you can try to do. But now we'll continue with examining the implications of this. And so if you have some object, well, first of all, one should be surprised by the fact that the black hole has a temperature, right? So the black hole is some geometry, it's a classical solution of some classical field equations, and now we're saying it has some temperature. So that's already a surprising fact. But to any system that has a temperature, we can calculate, we can then assign an entropy, and we calculate the entropy using the first law of thermodynamics, right? So we write ds equal to dm or dE over T, and we know the mass of the black hole as a function of Rs, so that's simply 2 g Newton mass equal to Rs. And we know the temperature function of Rs, so we can calculate the entropy. And when you calculate the entropy for this case, you find 4 pi Rs squared over 4 g Newton. And this is equal to the area of the horizon divided by 4 g Newton. G Newton can also be written as L Planck squared. So this is the area of the horizon in Planck units. So here I derived this for the Schwarzschild black hole, but this formula is true for any black hole, for charged black holes, rotating black holes in any dimension, as long as you can describe the system using Einstein gravity with some extra matter or whatever, you get this simple formula. Okay, so that's the black hole entropy formula. It's again related to a geometrical feature of the Schwarzschild geometry. And there are a couple of things that are noteworthy. So one is that it grows faster than the mass. So since the mass is proportional to R and the entropy is proportional to R squared, we are finding that this entropy is growing like the square of the mass. So it's more than extensive. It's not that as you add energy. So in ordinary condensed matter systems, if you have a block of material and you add some extra mass to the material, typically things will grow. The entropy will grow linear in the mass or linear in the volume. But here it grows faster. Also, this combination, Rs over L Planck squared, so actually the inverse of that combination, so L Planck squared over Rs, is the effective coupling of gravity when we view it as an effective field theory. So if we want to describe the black hole, we want to, for example, quantize or describe general relativity around the black hole background, the effective coupling is of order g Newton in units of the typical size of the system, which is Rs. So that's the effective coupling. And we know that the formula is proportional to the inverse of the effective coupling. So this is the effective h bar of the system. And we see that the entropy goes like 1 over h bar. So it's also a funny feature. And in the limit, when h bar goes to 0, when this parameter goes to 0, the entropy goes to infinity. So we see that geometry is doing a thermodynamic computation, and we would like to understand how it does that and why it's doing this thermodynamic computation. Now, the fact that geometry is doing a thermodynamic computation is also quite clearly seen if we consider Euclidean black holes. Okay, am I advancing a little? I started at, what time did I start? 11:20. Okay. So that fact is also seen clearly if we consider Euclidean black holes. And I'm going to perhaps go a little fast over this. So we can, if we consider, we make time there Euclidean, and we give it period beta, the same beta we computed here, we'll find that the geometry is of the time. Now this is Euclidean time, which is I times the time I defined over there. And this is the radial coordinate. And the geometry of this is a geometry of a cigar. So at the origin is where the horizon was sitting. But after we did that, did this continuation, this looks like the origin of the plane. So we have a completely smooth geometry. And we can compute the gravitational action of this configuration and define a partition function where this is the gravitational action, and reinterpret this as a thermodynamic computation. So this is just the definition of F. And if we take this F and compute the entropy from this F, we get this formula for the horizon area. And that's another way of deriving this formula for the horizon area. And one can understand, using properties of general relativity, that you get a result which is proportional to the area of the horizon. Okay. So we had this question of what this entropy is counting, and there is some evidence. There was some expectation, and I'll discuss the grounds for the expectations later. There was some expectation that this should describe the entropy of some microstates, which are all the possible states in which the black hole can be in. So somehow the black hole can be in many different states, different microscopic states, and when we average over these states, somehow we get some average effects which are encapsulated by this geometry, and this geometry is doing the thermodynamics for us and is counting those microscopic states for us. Now, in string theory, one can actually count these microstates in a different way and get an answer which agrees with this entropy formula. And I'm not going to go into the details of how this is done, but I would like to give you the spirit of the calculation. So somehow the logic for how you do it and the spirit. So the simplest cases here is to consider the 10-dimensional superstring theory and consider a supersymmetric compactification of the theory. So you go down from 10 to, let's say, 4 or 5 dimensions. And then you consider extremal charged black holes. So let's first consider charged black holes. So in these theories, there are some Maxwell fields, some U1 fields, and you consider black holes charged under those U1 fields. And for such black holes, having a smooth horizon implies that the mass should be bigger than the charge. And when the mass is equal to the charge, you have a so-called extremal black hole. And these are black holes for which the temperature is actually 0, but they still have a horizon and have an entropy. And you can compute the entropy of these black holes using the area formula. Now you can okay, and then so you have your charged black hole. It has some charge, and there is some formula for the entropy in terms of the area, and you write the area in terms of the charges. And the formula will involve the some integers, which are so these charges are quantized, and so it will involve the integer values of these charges. So a typical formula, for example, will be in 4 dimensions, something like n squared, where n is the integer values of the charges. Now you start with this black hole, and then you vary the parameters of the compactification. So you vary the size of the space in which you compactified it, and so on. And you can go to a situation where and you track the objects with the same charges, and these objects with these given charges become a system of branes, so some kind of branes that are crossing and so on. They are wrapped in internal dimensions. I won't go into the details, but the point is that this system of branes will now be weakly coupled, and you can calculate the number of configurations of these branes, of states in which these branes can be put. And so there is that number of configurations, and the log of this number of configurations agrees with the entropy you computed here. And you can also argue that in these supersymmetric compactifications, this process of deforming the geometry does not change the number of states. So that's something for which you rely on supersymmetry. But anyway, so this type of counting leads to well, you can do a lot of checks of black hole entropy formulas, and not only can you check the area formula, but so this is a number you can, in some cases, you can compute exactly, and then expand it for large values of the charges, and you get area over 4g Newton plus some corrections that are due to the contributions to the entropy due to the quantum fields propagating on the black hole background, etc. And then you can compare those corrections to this brane computation, and in the cases where you can compare, you get agreement. Okay. So this is some evidence that this area formula is really counting the microstates of the black hole. It's also non-trivial evidence that string theory is really defining, is a consistent theory of quantum gravity, is describing black holes in a consistent way. So this is a check that goes beyond string perturbation theory as described yesterday by Ed Witten. So, okay, now I'm going to discuss a topic which seems a priori disconnected, but with what I've been discussing so far, and then we'll try to discuss the connections. So I'm going to make a few remarks on entanglement. So you all know that you can have entangled states. You can have two physically separated systems, A and B, and you can have a pure state in A and B. And when you make measurements on A and measurements on B, these measurements will be correlated, and they're correlated in a way that is stronger than any classical system can be correlated, as said by the Bell inequalities. By the way, there was a test of Bell inequalities in particle physics by considering the BB bar oscillation system. But of course, there are the more famous tests using photons. But anyway, so that's just entanglement. And sometimes one can quantify the extent of the entanglement by thinking, so there is some Hilbert space where for system A and some Hilbert space for system B. and there is a total Hilbert space, which is the product of these two. And we have a pure state that lives in that total Hilbert space, psi, which belongs to that total Hilbert space. And we can define a density matrix for system A, which consists of tracing over the Hilbert space of B. So this is simply saying I forget about B and I look only at A, and I get some density matrix, and then we can compute. So it's not a pure state, it's a mixed state now, and we can compute the entanglement entropy for rho A. And this entanglement entropy quantifies the amount of entanglement that you have. Of course, for a spin system, which is in a pure state, so let's say the singlet state, for example, of two spins, we should get the usual log2 factor from this calculation. Now, the interesting fact is that the vacuum of quantum field theory is, in some sense, a very entangled state. So, if, for example, in quantum field theory, you consider a region of space A and the complement, and you define B to be the complement of that region, and you were to do this computation, you would find a very large, actually infinite in the field theory limit, entanglement entropy between A and B. And this is because if we think of the quantum fields as arising from local degrees of freedom at every point in space, the quantum field theory vacuum, those local oscillators that you have have wave functions which are spread all over space, and you have this entanglement between the, let's say, oscillator at this position and the oscillator at that position. Now we can see this a little more clearly. So I'm going to do one example of this. So if we go back to this, we go back to flat two-dimensional space, or maybe even four-dimensional space, but we consider the x minus and x plus coordinates, and then there are two transverse coordinates. We can imagine you consider only half of space. So you consider only this half of space, and you ignore all the other half. So you restrict to doing measurements only on this part of space-time. Of course, those are the measurements that, if you are an accelerated observer, those are the measurements you will do. But let's consider those. And for those, it's reasonable to consider to consider these Rindler coordinates and to look at the state in Rindler coordinates. And we've seen that the state in Rindler coordinates is a thermal state. So the density matrix restricted, so if A is this region, that rho A density matrix is just simply the usual thermal density matrix for the boost Hamiltonian, for the Rindler Hamiltonian, which let me call it K. Okay, K is the Hamiltonian that shifts the time t, the Rindler time t, and this is the ordinary thermal density matrix for that. So that's, I'm just restating the same thing that I said before, but slightly more formally. And we can calculate the entropy of this density matrix. It's just, and I'm going to do a hand-waving calculation. So we imagine you have a massless field on this space, and well, this two-dimensional space plus the two transverse coordinates. And we've seen already that the temperature is proportional to 1 over rho. So the entropy density is proportional to 1 over rho cubed. And then, so we can compute the total entropy, which will be given by integrating this 1 over rho cubed over space. The integral over the two transverse dimensions gives us just the area of the two transverse directions. And then we're left with an integral over rho of 1 over rho cubed between infinity and 0, but it's divergent at 0, so I'm going to put an ultraviolet cutoff, so it gives something of the order area over epsilon squared. Okay. So the fact that this UV divergence is the fact that I mentioned before, that there is a large amount of entanglement already in the vacuum. Now, this concept of entanglement entropy has been very useful in recent years for analyzing aspects of quantum field theory. One can subtract these divergences and define a kind of renormalized entanglement entropy that has lots of nice properties, like decreasing under the Archie flow, etc., etc. But well, that's a side comment. But now one popular idea has been that perhaps this entropy is somehow related to black hole entropy. So this is a vague idea which so you have this atmosphere, thermal atmosphere of the black hole, and it definitely contributes to the entropy. And it contributes naively an infinite amount. And if you were to put the epsilon equal to L Planck, then you get some formula which naively has the right value. But that idea has never been made precise. And in fact, the conservative approach, the conservative point of view is to say that this is computing a correction to black hole entropy. So it's a correction which is independent of the Newton constant. And that these diversions we're finding is cancelled by renormalization of the counter terms that you have in the Einstein action. It's coming from the counter terms you have in the Einstein action, and that cancels these diversions. And there's been some discussion of how gravity, maybe there is a miracle and gravity regulates these diversions. But we actually know how gravity regulates these diversions. In fact, and it's kind of instructive to understand how it works. So you, I mean, we discussed, so we had this picture for Lorentzian Rindler space, but we have a similar picture in Euclidean space. So in Euclidean space, we said that we had this Euclidean temperature. So this is now the Euclidean version of this space. So we have the ordinary polar angle, which goes from 0 to 2 pi, and that's computing just the trace of the density matrix. So if we wanted to compute the entropy, we would need to vary this temperature. So we would need to consider the quantum field theory on conical spaces, where the angle is not quite 2 pi, but a little smaller than 2 pi, and then taking the derivative, and then take the derivative. So we are led to quantum field theory on a cone, and since there is here a geometric singularity, that's why we are getting these diversions. But in gravity, we are not allowed to consider the gravity partition function on an arbitrary space. I mean, the space should somehow be a solution of the equations. The best we can do is fix the geometry far away and say we have a big circle whose length we fix, and we can vary then this total length. And then the space fills in however way, in a way that solves the Einstein equations. And when you do that, then if you fix just a circle far away, you might think that, let me draw it this way. You fix the circle at some regularizing surface, and you might think that in the field theory approximation you would have a cone, but the gravity solution is just simply an ordinary disk, and varying this size just simply varies the size of this disk. And if you calculate the gravitational action of this disk, you just get something equal to, well, it's just simply the area, the ordinary gravity formula. There are two transverse dimensions that don't contribute to this, so you get the area of the transverse dimensions, and then an integral over this two-dimensional disk. But as Ed Witten also mentioned yesterday, this is a topological invariant, and so we get some answer which is independent of beta, so proportional to the area. And well, that's essentially the same as the ordinary Hawking calculation. So this gives us actually the full answer in gravity, gives us a finite answer. So in some sense, gravity is regulating these UV diversions, but in a way that removes the statistical interpretation, right? So in order to have the statistical interpretation, we wanted to have this space-time and this temperature that was varying, and we could interpret this as the trace of something. However, when we consider this Euclidean gravity thermodynamics, we lose that statistical interpretation. But it gives us the full answer. So how to have both the finite answer with the statistical interpretation in a completely general framework is not understood. Okay. I now want to discuss another property of black holes, which actually relies on some interesting properties of this entanglement entropy. And that's the second law of black hole thermodynamics. Or the second law of thermodynamics. So let's start with an apparent problem, which is the following. Imagine you have a black hole. So you have a black hole, and you have some matter outside. Okay, so you have some system outside the black hole, and let's say you have some hot water here, and you now send it to the black hole. Okay, so it falls into the black hole, but this hot water had some entropy. So it looks like you're throwing the entropy behind the black hole horizon, and now the entropy outside of the matter outside the black hole has decreased. Okay? So this is an apparent. Now, from the point of view of the outside, it looks like a violation of the laws of thermodynamics, of the second law of thermodynamics. You might not be too bothered by this, because you might think, well, it went into a second asymptotic region, so I don't care. So, of course, if I'm only in this room and I take something out of the room, the entropy of the room could decrease, of course. Right? But this went into a region that has then no causal contact with the outside, so it's a little more bothersome. It was by thinking about problems like this that Bekenstein came up with the idea that the entropy would be there would be an additional entropy of the black hole, which is the area, and that you have to include that in the total count of the entropy. So the entropy should be the area over 4g Newton plus the entropy of matter outside. So this is the matter entropy. So in the thought process that we discussed, this would decrease. But then he said, well, since we are sending in something else to the black hole, the black hole mass will increase a bit, and the area of the black hole will increase also. So therefore, the second law might be preserved. Okay? Now, that would work as long as sending some entropy also implies you should always send some energy, right? So you should have you should not be allowed. Imagine you can put lots and lots of entropy in something which has very, very low energy, right? Then you could suddenly violate this. So you need that just the matter itself obeys a condition which says that the entropy of matter, of some system of matter, let's say this little system of matter, should be less than the energy of that same matter times its size. Okay. The size comes, I won't explain in detail because we'll see in a second a better version of this bound, comes from the fact that I won't explain exactly where it comes from. But let's say he had a bound like this, and this is called the Bekenstein bound. And it does not involve gravity. It does not involve g Newton, right? And so one question that people asked was, well, first of all, is this obeyed by all field theories? Is it obeyed by any system? What are the assumptions that go into proving this formula? Now, naively, let's say in non-relativistic systems, you can certainly violate it. So, for example, you can have a spin. You can have a, let's say, a spin with with very small energy and lots of spin degrees of freedom, so the entropy would grow like the log of that number of spin degrees of freedom, while the energy would be fixed. So maybe it's a property of relativistic quantum field theory. And in fact, there were some recent arguments that, first of all, made this bound a little more clear and also proved this bound as a consequence of general principles of relativistic quantum field theory. This was done by Cassini a few years ago. And the idea is the following. So the improved version of the bound is the following. So you first consider Rindler space, and you consider some system of matter in the right-hand side of Rindler space. And you consider now the entanglement entropy of two configurations. So one is, so you consider these lies, and we are going to consider these lies with the extra matter and without the extra matter. Okay? So when we had the vacuum, we are not doing anything. We already have some entanglement entropy, which is what we discussed so far, between the outside and the interior. And when we have matter, we might have some additional entanglement entropy, because if this matter has some entropy, of course this matter could be entangled with some matter on the other side, and we could have some additional entanglement entropy. So the entanglement entropy of this and this configuration need not be equal. In fact, we can have more entanglement entropy here. But unfortunately, these two are UV diversions. They have these ultraviolet diversions at this point, but the difference is finite. And so he says, well, the correct bound is the bound on the difference of these entanglement entropies and the expectation value of the difference of the Rindler Hamiltonians. So this is the difference. Maybe I should call it like this. This is the difference in the expectation value of this Rindler Hamiltonian. So that's the Hamiltonian performing these time translations in the vacuum. So that will give you something. And then in the system with the extra matter. Okay? And so this is a new formulation of this bound. And the nice thing about this formulation is you can actually prove it in general by using general quantum information techniques. In particular, you are using a certain entropy inequality of something called the relative entropy, which says that if you have two density matrices, then the trace of rho log rho over sigma is always bigger than 0. So by starting with this and choosing rho and sigma to be the rho of this right-hand side plus the matter, and sigma to be the one of the vacuum, then it's a simple matter to show this inequality. Okay? And then once you have this inequality, you can see that this inequality implies the second law of thermodynamics. That was done by Aaron Wall just recently. Okay? So notice, so the point, maybe this discussion was a little technical, but the point I want to convey is that non-trivial properties of quantum fields, of relativistic quantum field theory, are important and crucial for making sure that black hole thermodynamics works. Okay? That black hole thermodynamics is consistent. Okay? Okay. Now I'll discuss a slightly different topic. Are there any questions? I'm going on and on. We haven't asked for questions. Are there any questions? So let me summarize. So I discussed a couple of things. So we talked about black holes and why they have a temperature, why they emit. Of course, this temperature is called Hawking radiation, why they emit Hawking radiation. And this comes from demanding that the horizon is perfectly smooth, and it's like any other point in space. And then we've gone on to discuss properties of entanglement in the quantum field theory vacuum, and how those non-trivial properties imply that the second law of thermodynamics is valid in processes involving black holes. Okay. Okay, so now I'm going to discuss some further things that were learned about black holes using techniques of string theory. And I will need to review for that purpose something called the gauge gravity duality. So this is something that has applications beyond black holes. Or sometimes it's also called ADS-CFT. Okay, this is the following thing. So imagine you, instead of having QCD, so you heard in this school lots of things about QCD jets and quarks and gluons and color, etc. Imagine that instead of having ordinary bosonic QCD, you had most supersymmetric, most SUSY QCD. So this is a version of QCD that has a maximal number of supersymmetries and so on, and it's conformal invariant. It's called n equal to 4 super Yang-Mills. And you were to consider it in the limit that the number of colors is large, and also in the strong coupling regime, in the regime where the effective alpha is much bigger than 1. Okay? So this is a regime where you would be emitting lots of soft collinear radiation, etc., in any process, blah, blah, blah. So it turns out that this theory in this regime is the same as quantum gravity or string theory or string theory on a 10-dimensional space. Recall superstring theory is defined in 10 dimensions, which is ADS5 times S5. So we started with an ordinary 4-dimensional quantum field theory, and we say that all its dynamics and so on is the same as the dynamics of strings or gravity in this particular 10-dimensional space. For what I'm going to say, we can forget the S5, so we'll only talk about the ADS. So if you're not a string theorist, you can forget about the S5 and also the fact that we have strings, and you just can consider gravity in ADS5. So what is ADS5? So ADS5 is some space which has the 4 space-time dimensions we started from. So these are the 4 space-time dimensions where the field theory lives, and has 1 extra dimension. So we have the 4 space-time dimensions. We have this extra dimension rho. And this factor is a factor that grows very much when rho goes to infinity and becomes very small when rho goes to minus infinity. And you can think of this as, again, a gravitational potential, right? It multiplies the time direction. And so, for example, if you were sitting here, you will see a gravitational force that pushes you in this direction. Okay, so this is a particular space-time, and you can consider in this space-time some black holes or black brains. So a simple thing you can consider is to raise the temperature of this space-time. So that's a space-time that has 0 temperature. And in that situation, what you find is that you get a black hole horizon at some distance, some finite distance rho. And so you have a black brain. So it has three spatial dimensions. And the idea is that these black brains are the same as a hot plasma in the gauge theory. So it's a hot plasma that is very strongly coupled, so the coupling is very strong. The coupling is strong in the regime where you can think about these black brains. And you can start translating between black brains and hot plasma. And of course, we already know one of the elements of the translation is that the area over 4g Newton is going to be related to the entropy. And I mean, when you have this hot plasma, you have the loss of hydrodynamics. And then this are related to the behavior of long-distance waves or ripples on this horizon. So if this is one of the space directions, then this horizon can have waves, long-distance waves, and then these waves propagate along the horizon, and they also dissipate. They fall inside the horizon. And that is related to hydrodynamics and its dissipative parts, like due to the viscosity and so on. So the point is that now what you should extract from here is that through this gauge gravity duality, you find that a black hole ends up being related to an ordinary quantum mechanical system. Okay. And we know the translations for different questions. So any question that you can ask, any question about the black hole as seen from the outside, about the outside of the black hole, can be translated into a question in this side, so a quantum field theory question. Okay, so we understand quite precisely the dictionary for things we see from the outside of the black hole. So if you, for example, you could consider sending in a particle to this black hole and asking what's the probability that a similar particle can come out of the black hole and so on. Now this gauge gravity duality is a conjecture, and there are there is a lot of evidence that it is correct. And there have been even some numerical computations in some systems where people actually managed to compute this, compare the area formula and even corrections to the area formula to the entropy computed using numerical simulations of the gauge system. Okay, so this is further evidence that black holes, even black holes that have a temperature, can be described from the outside as ordinary quantum mechanical systems. Okay? So this adds to the evidence that, well, the second law was valid. Now we have these microscopic descriptions which tell us how to ask, in principle, any question that you can see from the outside. And one important property of this is that this respects unitarity. It's just ordinary unitary evolution. And we don't lose any information. So we never have information loss. So let me try to discuss what this issue of information loss is. Are there any questions? But before I start discussing that, are there any questions about this? Are you referring to the first blackboard? Yeah. So we saw that geometry is related to thermodynamics. That's the entropy. We saw that in order to make thermodynamics work, the second law of thermodynamics, we needed interesting properties of entanglement in quantum field theory that were investigated independently of this issue. Right? So that's one connection with entanglement. We also saw that the entanglement of quantum fields around the horizon certainly are important for understanding the corrections to the entropy formula. And we'll later see more connections between, the connection between geometry and entanglement is not very clear so far. It will become more clear at the end. Other questions? Okay. So I'm now going to discuss some aspects of the black hole information problem, or what's well, what is the black hole information problem, basically? So this is the following. So imagine you send some matter in, and you send some matter in, and you prepare the matter in a pure state or in a small number of states, initial states. Then you form a black hole. This black hole starts emitting radiation. It emits this thermal Hawking radiation. And at the end of the day, you end up with this radiation. You only have this radiation. Okay? Now, if you have unitary evolution between the initial state and the final state, then you should find that this radiation should be in a pure state. Okay? Now, it might be in a very complicated pure state. So, for example, if you well, in the LHC, you start with two protons, which are in a unique, essentially unique state. You collide them, and you get a mess. And it's a very complicated mess, but that mess are different projections of a unique, or essentially unique, initial pure state. Now, of course, if for more macroscopic things, that the mess could be even bigger, as happens when we, burn something and so on. But the question is whether, in principle, there is some formalism or there is some way of doing the calculation that allows us to go from this collapse to the radiation in a way that it maintains the purity of the radiation. Now, why would you call this into question? Well, it's because when you look at how this radiation is produced, so you have, I'm now going to draw the so-called Penrose diagram of a black hole. So there is a so it's similar to the flat space diagrams we're drawing, but there is some singularity here in the future. Not explaining all the aspects. Well, we don't need this so much. So we have the asymptotic region far away from the black hole, and it turns out that if you start with two trajectories which are very close to the horizon, they will diverge as time progresses. And the trajectories of these particles are essentially the trajectories of the particles that are created by the Hawking process. And so when you have the Hawking process, what happens is that you have these two particles that were some virtual pair, part of this entanglement that you had in the vacuum. And one member goes out to infinity, and the other member goes into the black hole singularity. Okay? So we started with a pure state here, and then we lose one of the members of the pure state, and we get the other one, right? So that process would produce the mixed state for this outgoing radiation. And recall that we had found this entanglement already in the vacuum. So if these pairs were not entangled, then we would not have the ordinary vacuum here. So having the ordinary vacuum here requires these pairs to be fairly entangled. So it seems that each time some particle is emitted, you are raising the entropy of the state outside, because you got the particle that comes in, and unless you somehow apparently violate causality or you do something strange, you will raise the entropy outside. And that was Hawking's original argument for why this evolution should not be unitary. So we should go from pure states to mixed states. He called that the dollar matrix, sending pure states to mixed states. I guess it's some physicists followed this path, and they were then blamed for the financial disasters and so on. But most physicists think that, The problem is that we wouldn't know what rules to apply if that were the case, and how to change the laws of physics in such a way, or how to change the laws of quantum mechanics so as to have a consistent evolution between pure and mixed states. And in fact, if you look at the gauge gravity duality, you see that here, if the gauge gravity duality is correct, then when you form black holes in the context of in anti-zeta space, for example, then we can translate any question of the black hole as seen from the outside to a question here, and in particular, this question of the evolution can be translated, and it leads to a unitary answer. Okay? So if the gauge gravity duality is correct, then the formation and evaporation of black holes in anti-zeta space should be described in a unitary fashion. So you have, let's say, anti-zeta space sort of like hyperbolic space or a space with a boundary. So you can form a black hole in the middle and let this black hole evaporate, etc. You have also formulations of, in some cases you have black holes which do not evaporate in anti-zeta, but you also have formulations of the information problem for those black holes, and if the gauge gravity duality is correct, those processes are described in a unitary fashion. Okay, so all that seems to suggest that black holes should evolve unitarily as seen from an observer outside. Okay, now however, the gauge gravity duality doesn't tell you exactly what happens in the interior. So it tells you what happens, how to ask questions. So it tells you that if you have any question that you can ask from the outside of the black hole, you can answer those questions. But you also have questions about the interior. So examples of questions about the interior are, what happens if I fall into a black hole and I hit the singularity? What really happens to me? What's the proper description of the singularity inside the black hole? Well, maybe I should say a few more words about the singularity inside. So if you recall the Schwarzschild metric, so we had the outside, we talked a lot about outside, and we can go inside by making R less than Rs. So this region here outside was R bigger than Rs, and inside is R less than Rs. Now when R is less than the Schwarzschild radius, then this sign changes, and this coordinate becomes a space-like coordinate, and the R coordinate becomes a time-like coordinate. Okay? So when we go to smaller values of R, we're going into the future. Okay? Now at R equal to 0, these coefficients of the metric diverge, and you can, in fact, check that the curvature actually diverges. So there is no coordinate transformation that would save you from this. And so at R equal to 0, you have a region where the space-time curvature goes to infinity. And so if you are an outside observer and you fall in, you will hit this region, and well, the ordinary laws of physics cease to be valid in this region, and you can wonder what happens to you. Okay? So that's a question we cannot answer. If we only look at the black hole from the outside, we don't know how to ask this question. Now, people have recently proposed many new versions of the information paradox. They are sometimes called the Firewall Paradox, and I probably will not describe them in detail unless someone desperately wants me to describe them. But they are further paradoxes that highlight our lack of understanding of the interior and are destined to try to rule out various ways of thinking about the interior. And it's called Firewall because these authors say that, well, there is some paradox, and they say, well, let's assume that there is no interior. And now that there is a firewall at the horizon. And now prove me wrong. Develop the right theory and prove me that there is no singularity at the horizon. Okay? And unless we develop the right theory and prove them that there is no horizon, no firewall, then we wouldn't have understood this problem. Or maybe there is a firewall. Maybe I'm wrong. There is a firewall. But we see a clash of two principles. One is the idea that the horizon is smooth, and the other is the idea that unitarity outside is preserved. And these two seem to be in conflict with each other, and understanding how this works, I think, will lead to further understanding of quantum gravity. Yeah.
So wasn't there a consistent description of black hole in string theory?
Yeah, so there is a consistent, there is a description from the outside. We can ask anything we want of the black hole as seen from the outside, and that description is unitary. Yeah.
You mean the one with the brains intersecting each other?
Yeah, that was only for the counting. And so, yeah, maybe I should have emphasized that. So that description with the brain and the counting, that was for the counting of these special black holes. A better description that allows you to think about dynamical processes and so on goes via this gauge gravity duality. Or there is something else called matrix theory, which also does the same thing. There you can ask any question about black holes as seen from the outside. And all those questions seem to work. I mean, you seem to reproduce many of the properties, the entropy, this viscosity, the hydrodynamics of black holes, and so on. So there are many things that work nicely. And so that leads you to have some confidence in the duality. The question, of course, of unitarity relies on a very strong version of the duality, which says that the duality is exactly valid, right? I mean, if black holes did not preserve information, then the duality would not be valid. There would be something wrong about the duality. Okay. But if you view the duality as a definition of the quantum gravity in the interior, with this definition, black holes are unitary as seen from the outside. But what could be is that with this definition also there is a firewall at the horizon. And so we have to understand well enough how to describe the interior to answer this question of whether there is or there isn't a firewall. Okay. And hopefully hopefully we'll understand some new aspect of quantum gravity to resolve this, to completely resolve in a completely satisfactory way this issue. Now, notice one interesting aspect of the interior is that the radial direction is a time-like direction, right? It's time, and so this looks like a big crunch cosmology. So the interior of a black hole looks like a kind of asymmetric big crunch cosmology. So the sphere is shrinking, and the time direction is not shrinking. But so understanding better the interior, I think, will probably help us understand cosmologies, and eventually we'll be able to understand the Big Bang and so on. These issues of black holes are not totally disconnected with cosmology. So, for example, this phenomenon of Hawking radiation was first discussed around black hole spacetimes, but essentially the same phenomenon occurs in the Sitter space, so in an expanding universe. There is again there a horizon, and we have this phenomenon of creation of particles and thermal fluctuations, etc. And that's the phenomenon we use for understanding the generation of cosmological fluctuations during inflation. So these are all things that are related. Normally, progress in one might help you understand another aspect of the other problem. And I think since the interior it looks like a cosmology, probably understanding the interior better in this setup will hopefully help us understand how to think about cosmology. Okay, so now I'll discuss something interesting about the eternal black hole. So this is a particular geometry which is the maximal analytic extension. So we saw here that we started with the Schwarzschild geometry, and we could go behind the horizon into the interior. But there is that bifurcation point, and there is some region to the left side. And when you look at what the whole diagram looks like, there is a cartoon which looks like this. There's a precise definition behind this cartoon, but I can't explain it very well. So this region corresponds to the asymptotically flat space region, so all of R3 or R3, 1, and the horizon. Okay, it's this line. Here inside we have the interior. Here we have a second asymptotically R3 region, so here is the infinity region. Okay, and here we have some past singularity, so it's time reflection symmetric. Now, just to clarify this picture, so for example, if you look at this particular time slice, so time goes in the vertical direction and space, the radial direction goes in the horizontal direction, and I'm suppressing the two sphere directions. So if we look at that spatial slice, so that roughly looks like this. So we have one spatial slice, which is this, and we go all the way to the horizon, so now we are here. And then on this side, we have something somewhat similar, and we again go to infinity. So we have here R3 at infinity, and here we have the horizon, which is a two-sphere. Okay, so this surface of the black hole is called the Einstein-Rosen Bridge. They were the first to notice that you could analytically continue through the horizon. This was even before it was understood that you could analytically continue through the horizon. Now the interpretation, so this is some space-time, and you can ask what is the interpretation of this space-time. And proposed interpretation of this space-time, this was first done by Israel, was that you should think of this as an entangled state of two black holes. So we have two black holes living in different space-times, and somehow, so we have all the states and of even the fields outside and so on of one black hole. These are the corresponding ones of the second copy. And we consider this pure state on the Hilbert space of these two separate space-times, right? So we have two completely separate space-times, and we have this particular entangled state. Now, this bar means the CPT conjugate. What is n? So n is a sum over all states, all possible states. It's some number that labels all the states. So we assumed that the black hole has a finite number of microstates, or finite number of relevant microstates. Of course, this sum could run to infinity, but since they exponentially suppressed, we could cut it off. So there is a finite number of relevant ones. They're indexed by some integer, right? This integer doesn't mean anything. It's what labels the various states, right? And this is the corresponding energy of each of the states. What's the bar? What is? The bar means the CPT conjugate, because so here, so let's say a Hawking mode that is coming out here is related to something that is going in this direction. So, okay. Now that spatial geometry of the Einstein-Rosen bridge can also be viewed as a wormhole, connecting two far separated distances of the same space. So you could consider now, let's say, a big R3 slice, and let's say you have one black hole here, and another black hole very far away. And now you can connect the horizon of this black hole to the horizon of this other black hole. Okay. Now this will not be an exact solution because there will be a small gravitational force between these two, but it's a good initial condition for the configuration, and you can essentially ignore this small gravitational force. So this is an interesting configuration. So there, the left and right hand sides are essentially living in the same space-time. So you have two black holes separated by a long distance. But if you're an observer here, you can go along, you will be separated by a short spatial distance, from an observer here through the black hole horizon. So let's say you are observer A and observer B. There is a long distance through the ambient spacetime, and then there is a short distance through the black hole horizon. So a short distance in this diagram corresponds to, so we have some guy A here, or let me call this B, and someone A here, and they are separated by a short distance, okay, in this spacetime. So one of these guys could be a black hole here nearby, and the other one could be a black hole, let's say, in the Andromeda galaxy far away. But if you are just outside this black hole, will be separated by a small spatial distance from B. So, yeah.
They should be inside the black hole. Inside the black hole is upper half.
Yeah, perfect. This is a good question. So that I should emphasize. So these two regions look like the outside of a black hole. They both look like an outside of a black hole. Yeah, you could call this the inside. I think that's what you have in mind. But here I'm drawing just, what I'm drawing here is this spatial slice, okay? For the moment, I'm drawing this spatial slice. And the spatial slice looks like this. So there is, that's the R3 spatial slice, and we can have a connection we can have this short distance connection or this long distance connection between these 2 points. Okay? So the topology of this slice is different than the topology of R3. Okay? Yeah. Now we can set this up as initial conditions in general relativity. So this is a good initial condition in general relativity, and then we let it evolve. And the evolution is essentially what we see in this diagram. And the interesting aspect of this evolution is that notice that the horizon of the two horizons coincide here, but they start separating. Okay? As soon as we start the evolution, they start separating. Also, the two spheres start shrinking as we approach the singularity. Okay? And essentially, that effect implies that if you send a signal from B to A, you want to send a signal from B to A, but A never receives the signal. So the space starts getting longer, and A will never receive the signal. Okay? Similarly, A cannot send the signal to B. So these wormholes, even though naively you might have thought that, well, they will lead to some non-local effects, actually do not allow you to send the signal. Okay? They do lead to some non-local correlations. So for example, we have seen that there is some entanglement between A and B, and if you consider, you measure some mode of the quantum, so you consider a field here, phi, right? And you consider the two-point function, phi at A, so this point A is some point here, and phi at B, this expectation value, that would be non-zero, right? That will go like 1 over the distance short. Let's say it's a massless field. Right? So there are correlations, but there is no way to send the signal. So the idea is that, again, this configuration can be interpreted as two entangled black holes. So you have the two black holes, and we are considering them in a very special state. That special thermofield state is a particular entangled state. I mean, it's special for two reasons. One is because they are entangled, and second, they are entangled in this particular fashion. Okay? It's the same as saying you have two spins, then they are in the singlet state, right? So that specifies completely the state they are in. And here we're saying the same thing. But here, in this example, entanglement between the microstates of the black hole has produced a whole new region of the geometry, has produced this non-trivial geometry that connects them. Okay? So that's that arrow that you were asking me before, between geometry and entanglement. So in this case, the entanglement between the two black holes has created this geometrical connection between the two spacetimes. Now there's one other interesting thing. So in principle, well, I haven't told you how to create this state. I have said, well, imagine you have two black holes in this state, right? Now, in the case of entangled states in quantum mechanics, you often, I mean, there are some ways of creating them. For example, you take two spins in the singlet, they could come from the decay of a spin zero particle, right? So that's one way of creating two spins in the singlet state that are separated. So here I haven't explained how to create this. There are some circumstances in which you can get black holes this way. It's always very difficult. And I'm not saying this is a practical way that you will be able to do this in practice. Probably you will not be able to do it very easily. But it's something that in principle, a configuration which in principle you could have. So as a thought experiment, you can consider this. Now, imagine you created this state, and we said that you could not send signals from A to B. However, one interesting fact is that you can so A can fall into the black hole, can go into the black hole, and then she can receive signals from B. Or if B goes in, he can meet A here inside. Okay. So even though you cannot send signals, you can still meet inside. Okay. So that's an amusing property of this geometry. Of course, once you go inside, you are not allowed to. You will not be able to. A will not be able to send outside the results of what B told her, right? So you might have thought that, well, maybe the interior, okay, classically maybe from the interior you cannot send signals to the exterior, right? But in this example, even quantum mechanically, you don't, or even if you treat it exactly, you don't expect to be able, A is not supposed to be able to send you signals from B without violating causality in a very strong way, okay? So the signals she receives from B. So really what you see in the interior of second point is that what you see when you fall into the interior of this black hole depends on what signal comes from the second black hole, right? It's not just a property of the initial black hole you had. So if you have some black hole and you fall into the interior, you might think that what you see inside only depends on the state this black hole is in, right? But in this case, it depends on what is it entangled with, right? So it might be in a mixed state. So this black hole, from the point of view of the observer in A, this black hole is in a completely mixed state, right? If he only considers A, it's in a completely mixed state. And you might think, well, if I fall into this black hole, I'm going to see just an ordinary black hole. But what you see actually depends on what B might or might not send you. Okay. So these are all different observations that are relevant for how to build a theory about the interior. So a complete theory about the interior. So all these are. So the interior somehow comes out of the entanglement between A and B, and it depends both on A and B in this example. Now, there are some situations where black holes are entangled not with a second black hole, but with radiation. So imagine that this is a very old black hole that has existed for a long time and has emitted a lot of radiation. It emitted more than half its initial entropy in radiation. So there will be these particles that correspond to the radiation. And this black hole will be entangled with these radiation particles. And people have said, well, if the black hole is entangled with the radiation, let me go back to this near horizon picture. So we had some modes, some quantum fluctuations of the field that if we want the field to be smooth, then they have to be entangled with the quantum fluctuations of the field inside the horizon, right? But if the black hole emitted radiation and the whole radiation system has to be in a pure state, then the early radiation has to be entangled with the late radiation, and this mode will give rise to some late radiation mode, late radiation. And so this guy has to be entangled both with the radiation and the fields inside. Okay? And this one theorem in quantum information theory which tells you that you cannot be maximally entangled with two other things. Okay? So it's called the monogamy of a maximal entanglement. Okay, so that's and this leads to this is one of the paradoxes that I alluded to, one of these so-called firewall paradoxes. But well, it could be that the radiation is one more thing. So I discussed these two black holes that were in this entangled state, and well, black holes are big macroscopic objects that have many degrees of freedom. But you could imagine that as a very wild extrapolation, if you have two spins and they are entangled, they are in your space, they are somehow united by a very quantum wormhole of some kind. What kind, I'm not telling you. So maybe also the radiation is entangled in some way with, well, the radiation is entangled, we know the radiation is entangled with the black hole, and then there are these very quantum wormholes whose nature we don't understand. But when they all join together, they might give rise to a horizon which is smooth, in the same way that here all the states of this black hole gave rise to this smooth geometric region of the horizon. Okay? So instead of having this region of the black hole, here we will have something where all those mouths of the little wormholes join in, but maybe we still have. But well, this is just a speculation. That's a way in which you could resolve this paradox, have something consistent with that paradox, and also consistent with a smooth interior. So, okay. Now, making this more precise, I leave it to you as an exercise. Okay. It was a joke. Okay, so I've reached the end. So the summary of this is that black holes connect thermodynamics, entanglement, and gravity in an interesting way. And I think understanding this will teach us more about quantum gravity. And well, I already said that the interior is like a cosmology, so once we understand properly the interior, we'll also hopefully understand cosmology.